Hey everyone! In this video, let's take a look at continuity and what it means for a function to be continuous. Now, one way we can think about continuous functions is that we can draw them without having to lift up our pencil. But that's not really a mathematical definition. So let's start by taking a look at the three-part definition of continuity. Now, as we're looking at this three-part definition, we're going to be focusing in on a certain number, a specific value, and we're going to call that C. The first part of the three-part definition is that my function needs to be defined at C. So in other words, f of C is defined. Another way we could say this is that that value for C has to be in the domain of our function. We need to be able to evaluate f of C. The second part of the definition is as we move closer and closer to that value of C, the limit has to exist. So the limit as x approaches C of the function, this needs to exist. So as we move closer and closer to that value of C, our y values also have to move closer and closer to some specific number. And then the last piece of the definition, bringing those first two together, is they need to be the same. So the limit as x approaches C, that value for the limit has to be exactly the same as that function value at C. So let me do a little visual just to help explain this a little more. So here's a curve. We'll say this is our function f of x. We're going to start off by picking out some number along the x-axis, and we'll call that C. So the first part of the definition is that this needs to be in the domain of the function. So I should be able to take this value of C, plug that into my function, and I should get a point that is on my curve. So then the y value here should be f of C. The second piece of the definition is looking at the limit. So looking at the limit, it needs to exist. So as I come from the left side and as I approach from the right side, along my curve, these two limits need to be approaching some value. So for this limit to exist, they need to be approaching the same number. And then the third part of the definition is bringing those first two together. And as we're taking a look at the limit, so not only are the two one-sided limits approaching the same number, but that number is f of C. So that's the mathematical definition for continuity. But beyond that, this also gives us a way that we can test to see whether or not a function is continuous at a specific value. So if any of these three things are not met, we would say that the function is discontinuous at that number. So why don't we test that out in an example? So here I have a function f of x, and this is equal to 3x squared minus 5x plus 4, and I want to test out, and I want to see if this is continuous at the value c is equal to 1. To test this out, we're going to use the three-part definition. So the first part is this value is in the domain of our function. Well, our function is a parabola, so it's a polynomial. So that means that our domain is all reals. If our domain is all real numbers, the value of 1 is certainly in the domain. So that means we should be able to take a look at this function value. So let's take a look at f of C, which is going to be f of 1. So plugging in 1, we have 3 times 1 squared minus 5 times 1 and plus 4. And simplifying this, we end up with 3 minus 5 plus 4. So at 1, our function is equal to 2. Okay, so it is defined, so that checks off the first box. The second piece of the definition is that the limit has to exist. So we need to take a look at the limit as x approaches 1. And as I said, our function is a polynomial. So that means to evaluate the limit, I can do that with some substitution. So substituting in 1 for x, and simplifying, we get 3 minus 5 plus 4, so we end up with 2. All right, so the limit does exist. And now the last piece of the three-part definition is that the function value at 1 and the limit as we approach 1, they have to be the same, which we can see they are both 2. So that means that yes, this is continuous at that value. So just to summarize this, we can say, so since our function value at 1 is exactly the same as the limit as x approaches 1, because those two things are both equal to 2, we know that our function f of x is continuous at this value of 1. All right, let's try one more. We'll do one that's a little bit more exciting. So here I have a piecewise function g of x defined by 3 different parts. So the top one, everything that's less than 3. In the middle, we have a value at exactly 3. And then the last piece is everything that's greater than 3. So again, we're going to use our 3-part definition to take a look at this. So the first one is we need to figure out if this is defined at g of 3, which it is. Because if I look at this at exactly x equals 3, we end up with this value of 9. So the second part of the definition, we need to take a look at the limit as x approaches that value of 3. Now, because this is a piecewise function, we are going to want to take a look at the one-sided limits. So let's start with the left-handed limit. So the limit as x approaches 3 from the left. And to do that, we're going to take a look at all the values of x that are less than 3. So we want to use that top equation, x squared minus 9 divided by x minus 3. Now looking at this limit, I can't just use substitution, because if I were to plug in 3, I would end up with something that's undefined. I would get 0 over 0. So we do have to simplify this a little bit. So in the numerator, that is the difference of perfect squares. So we can factor that into x plus 3 and x minus 3. And now written in factored form, we have a common factor that will simplify. So our limit is the same as the limit as x approaches 3 from the left of just the expression x plus 3. And now written like this, now this is a simple polynomial, and we can just substitute in 3 to evaluate the limit. So 3 plus 3. So this one-sided limit is equal to 6. Now let's do our right side limit, the limit as x approaches 3 from the right. And in this case, we want to use all the values of x that are bigger than 3. So we're going to use the bottom equation of the x squared minus 3. This one is already a polynomial, so we can evaluate this one with substitution. So this will be the same as 3 squared minus 3, which is 9 minus 3, and we get 6. Okay, so our two one-sided limits are the same. They both ended up as 6. So that does mean that our limit exists. And overall, our general limit as we approach 3 is equal to 6. But comparing that to our function value, it's not the same. So because our function value at 3 and our limit as we approach 3 are two different numbers, we would say that this is discontinuous. So to summarize that, let's say, so because g of 3 is not equal to the limit as we approach 3, our function is discontinuous. So I want to finish up by sketching a graph of our piecewise function just so we can take a look and visualize what this discontinuity looks like. So I'm just going to work my way from left to right. So starting with our top equation, for everything where x is less than 3, we're going to use the x squared minus 9 divided by x minus 3. Now as we saw when we were working with our limit, that does simplify to just x plus 3. So that is a line with a y-intercept of 3 and a slope of 1. So it's going to look something like this. Now once I get to 3, so at this value of 3, this graph will have a hole there, not only because that's where our switch is happening, but because that x minus 3 simplified. So this would have a hole no matter what. So let me connect those with a line. Okay, so that takes care of the first piece. Now in the middle, at exactly x is equal to 3, we have this value of 9. So exactly at 3, our function is going to be up here with 1 point, and this is up here at 9. So this one, just to compare, this is going to be at 6. We know that's 6 from the limit, but I could also plug in 3 to see what we'd end up with there. And then right on the other side of 3, we're going to pick up with that last one. So that last one, x squared minus 3, that's going to be a parabola shifted down 3 units. So just to see where this starts off, we know that because of the limit here, it's going to start at 3, 6. Again, it's going to be a hole. It's going to be an open circle because we don't have the or equal to part. At 4, we would be at the point 4, 13. So this is going to shoot up pretty quick, but it's a little piece of a parabola like so. So if we look at our graph, this is almost a continuous function. However, as we move along from left to right, so as I move along this green line, once I try and join up with the parabola, there's a hole there. So the thing that's making this discontinuous is the fact that the limit as we approach 3 is not the same as the function value at